It happened in the middle of the night, roughly 80 to 100 miles off the southern Oregon coast, on the floor of the Pacific Ocean, where no one was around to feel a thing, a magnitude 4. Then, within seconds, a second jolt nearby. Then, within the same half hour, a third. 3 earthquakes clustered in the same patch of ocean, all in a window of time short enough that seismic monitoring stations up and down the west coast picked up the alerts almost back to back. No one on land felt any of it. No damage, no tsunami warning, no breaking news alert on anyone's phone. By almost every measure that matters to an ordinary person going about their day, this was nothing. And yet, 2 days later, seismologists were still talking about it. Not because the earthquake itself was unusual, moderate quakes happen in that stretch of ocean all the time, but because of what surrounded it, what came right after it, and strangely enough, because of one thing that was conspicuously missing from the data. To understand why a professional monitoring network would spend 2 full days poring over a sequence of earthquakes that nobody on land even noticed, you first have to understand exactly what kind of coastline this is and why the people who study it never quite relax. The Pacific Northwest has spent roughly the last 3 decades slowly and publicly coming to terms with a piece of geology that most residents didn't fully understand until fairly recently. Sitting just offshore, running for about 700 miles from Northern California up through Oregon and Washington and into British Columbia, is something called the Cascadia Subduction Zone. It's the boundary where the Juan de Fuca oceanic plate is being forced, slowly and relentlessly, underneath the much larger North American continental plate. Subduction zones like this one are capable of producing the largest earthquakes the planet can physically generate, magnitude 8, 9, occasionally larger, because instead of rupturing along a short, contained stretch of rock the way most faults do, a subduction zone can fail along hundreds of miles of its length all at once, releasing a quantity of stored energy that dwarfs almost everything else in nature outside of a major asteroid strike. Cascadia has done this before. Scientists know almost exactly when, and the story of how they figured that out is one of the more remarkable pieces of detective work in modern Earth science. On the night of January 26, 1700, the fault ruptured along its full length, producing what researchers now estimate was a magnitude 9 earthquake, one of the largest ever recorded anywhere on the planet, even though no instrument on this continent recorded it directly because none existed yet. The evidence survived anyway, in 2 completely separate forms, thousands of miles apart, that only made sense once researchers connected them centuries later. Along the coast itself, indigenous communities had passed down oral histories for generations, describing a night of violent, extended shaking, followed by a flood that swept far inland and wiped out entire villages. For a long time, outside researchers treated these accounts as folklore rather than data. That changed once geologists started finding physical evidence that matched the stories almost exactly. Layers of sand deposited far inland by an enormous wave, and whole groves of cedar trees still standing dead upright, killed the instant the coastline dropped several feet and salt water flooded their roots. On the other side of the Pacific, in Japan, meticulous historical records from coastal towns described an unexplained tsunami that arrived on the shores of Honshu in the early hours of January 27, 1700, with no earthquake ever felt locally to explain where the wave had come from. Japanese researchers spent years trying to work out what could generate a wave of that size, with no accompanying shaking on their own coastline. The eventual answer was Cascadia, nearly 5,000 miles away. A fault whose rupture sent a tsunami racing clean across the Pacific and arriving in Japan roughly 10 hours later, all of it faithfully logged by officials who had no idea what had actually caused it. That single connection, an unexplained tsunami in centuries-old Japanese records matched against unexplained sand layers and dead forests on the Oregon and Washington coast, is how scientists dated Cascadia's last major rupture to that specific night with a level of precision that still surprises people the first time they hear it. Researchers didn't settle for a rough year. Working backward from the confirmed arrival time of that tsunami in Japan, combined with known travel speeds for tsunamis crossing open ocean, they calculated the earthquake's origin time to within a few hours, and estimated its magnitude based on how large the wave needed to have been at the source to still arrive at the height that was documented on the far side of an ocean. It remains one of science's more striking examples of 2 completely independent record-keeping traditions, an oral history passed down through generations on one continent, and a written bureaucratic log kept by officials on another, turning out to describe the exact same event, neither where the other existed, until researchers pieced it together 3 centuries later. When scientists later went digging even further back, using core samples pulled from the seafloor and from coastal marshes, they found evidence of dozens of major earthquakes on this fault system, stretching back roughly 10,000 years. That gives them a rough average interval between ruptures, and it places the fault somewhere inside its expected window for the next one, with real, significant uncertainty about exactly where inside that window things currently stand. That's the earthquake people mean when they talk about the big one. A full-length rupture is projected to produce shaking that lasts minutes rather than seconds across the entire Pacific Northwest, followed by a tsunami that could reach heights of up to 100 feet in the most exposed coastal areas, arriving in some communities in under 15 minutes, faster than a lot of current evacuation plans assume people are capable of moving. So when the ground shifts off the Oregon coast, even a little, even nowhere close to catastrophic, the instinctive question for a lot of people isn't really about the specific number reported. It's whether this is finally it. Here's where the story this time takes its first real turn, because the actual location of these earthquakes tells a very different story from the one the initial fear suggests. This sequence did not occur on the Cascadia subduction zone at all. It happened on something called the Blanco fracture zone, a completely separate fault system sitting further out to sea, and geologically almost nothing like the subduction boundary everyone has spent decades being trained to fear. The Blanco fracture zone is a transform fault a couple hundred miles long, running roughly northwest to southeast, connecting two undersea volcanic ridge systems, the Gorda Ridge to the south and the Juan de Fuca Ridge to the north. Rather than one plate sliding underneath another, the way Cascadia works, the Blanco system involves two plates grinding directly past one another, side by side. A sideways strike-slip motion similar in basic mechanics, though on a larger scale, to California's famous San Andreas Fault. Geologists describe it in fairly blunt terms. It's simply where two tectonic plates offshore are sliding past each other. And it happens to be one of the most seismically active fault zones in the entire region precisely because of that constant grinding. Once you look at how often this stretch of ocean floor actually moves, the picture becomes almost mundane compared to the fear that spikes the moment a headline mentions an earthquake off Oregon. The Blanco system produces hundreds of earthquakes every single year. Most are small enough, below magnitude 3, that only sensitive instruments ever detect them. No human being ever feels them. Moderate quakes in the 4 to 5 range happen with real regularity here, several times a year in a typical stretch, occasionally clustering into swarms of a dozen or more events within days, exactly the pattern this latest sequence followed. Even larger events aren't unheard of. Earthquakes in the magnitude 6 range have struck this same zone multiple times over the past decade, including one that hit with no damage or injuries at all. There was even a stretch of recent years when more than 50 separate earthquakes struck the same fracture zone within a matter of days, the largest peaking around magnitude 5. 8, generating headlines of its own, and agencies confirmed almost immediately that it posed no tsunami risk whatsoever because of exactly where and how it occurred. The reason for that difference comes down to basic physics, and it's worth understanding clearly, because it's arguably the single most useful piece of information in this entire story. The one fact that, if more people understood it, would prevent an enormous amount of unnecessary panic every time this coastline shows up in the news. A subduction zone earthquake, the kind of full Cascadia rupture would be, involves an enormous, gently sloping fault surface hundreds of miles long that can fail all at once, lifting or dropping huge sections of seafloor vertically. That's exactly the kind of motion that displaces massive volumes of ocean water and generates a wide, devastating tsunami. A strike-slip fault like the Blanco system, by contrast, involves two plates sliding horizontally past each other rather than up and down, motion that, even at significant magnitude, doesn't shove large volumes of water vertically in the same destructive way. Think of the difference between a trap door swinging open beneath a swimming pool versus two glass panels sliding past each other at the pool's edge. Both involve real force, only one of them moves the water. That's precisely why, even during earthquake swarms on the Blanco system involving dozens of moderate quakes and peak magnitudes above 5, monitoring agencies have consistently and quickly confirmed no tsunami threat, and why official guidance states plainly that earthquakes below roughly magnitude 6. 5 on this particular fault system are very unlikely to generate any tsunami at all. So here is the honest, straightforward answer to the fear that spikes every time a moderate earthquake rattles the Oregon coast. This specific sequence had nothing to do with the Cascadia subduction zone, posed no tsunami risk, and does not represent the beginning of the big one this region has spent decades bracing for. Researchers who study this coastline for a living have been explicit about exactly this point after similar swarms in the past. Blanco fracture zone activity comes from an entirely separate offshore fault and has nothing mechanically to do with the far more dangerous system everyone considers overdue. That could be the end of the story. A moderate, unremarkable earthquake sequence on a fault that produces them constantly, correctly identified, correctly ruled out as any kind of serious threat. Case closed. Except that isn't actually why researchers kept watching this region as closely as they did in the days that followed. Because underneath the specific sequence that just happened, 3 other things were quietly unfolding at the same time, and one particular silence sat on top of all of it. Let's go back to the exact sequence itself because the details matter. Roughly 8 seconds after that initial 4. 9, a magnitude 4. One struck about 30 miles to the east at a shallow depth of around 5 miles. 2 events, 8 seconds apart. Neither felt on land. The motion involved in that part of the fault system runs sideways rather than vertically, which is exactly why there was never any prospect of a tsunami and no advisory was issued. What made monitoring networks lean in wasn't those 2 events themselves. It was what showed up in the 90 minutes that followed, and then across the next 48 hours on fault systems well inland. Roughly 90 minutes after the offshore sequence, a small magnitude, 1, 4, earthquake registered on instruments positioned inland in the corridor where the Gorda Plate is being forced down beneath North America. Later that same day, a magnitude 2.0 was recorded at a depth of about 14 miles, near the southern portion of the Cascadia subduction zone itself, followed by a 2. 1 near the California border and several smaller events scattered across southern Oregon. On paper, a 1.4 and a 2.0 are nothing. You wouldn't feel either one standing directly above it. But there's a specific detail about that 2.0 that matters enormously. It was recorded at roughly 14 miles depth, placing it at or very near the plate boundary itself, rather than in the shallower crustal faults sitting above it. And here's why that's significant. The plate interface off the Pacific Northwest, the locked surface that will eventually produce the region's next megathrust earthquake, is seismologically almost completely silent. It doesn't tick away with frequent small earthquakes the way California's San Andreas system does. So when an event does get located right on or near that interface, at the correct depth, it stands out simply because it's unusual by definition. One small earthquake isn't a signal on its own, and there's real uncertainty in how precisely depths get calculated in that region. Any honest account has to say that plainly, but it's exactly the kind of detail that makes experienced seismologists look twice, and on this particular occasion, several of them did. So the obvious question came up almost immediately. Did the offshore sequence somehow nudge the Cascadia megathrust closer to failing? The answer, based on the published science, is no. Not maybe, not probably, no. And the reasoning is worth walking through carefully, because it's solid physical explanation rather than reassurance for its own sake. Monitoring networks have dealt with this exact question before, after events considerably larger than this one. A previous swarm on the Blanco system included dozens of earthquakes, more than a dozen above magnitude 5, 2 of them above magnitude 5. 8. With combined energy release comparable to a single magnitude 6. 3 quake. The published conclusion at the time was that slip in those events was unlikely to have caused any meaningful stress change on the Cascadia subduction zone, roughly 125 miles closer to shore. 2 reasons explain why. The first is distance. The permanent mechanical nudge one earthquake delivers to surrounding rock, what scientists call a static stress change, doesn't travel far. It falls off sharply, roughly on the scale of a few multiples of the rupture's own length. A 4. 9, like this one, ruptures something on the order of a mile or 2 of fault. The nearest locked portion of Cascadia sits roughly 125 miles away, something like 100 rupture lengths of separation. Whatever stress change arrives at that distance is not just small, it's functionally zero. The second reason is the rock itself. The crust out at a spreading ridge like the Gorda Ridge is geologically brand new and still hot, and it behaves fundamentally differently from older, colder, stiffer rock. One of the more memorable descriptions monitoring scientists have used compares it to a fresh cookie straight out of the oven. Push on one side and the other side barely notices, because the material absorbs the energy instead of transmitting it cleanly through. Published analysis has gone as far as stating that even a magnitude 7 on the western portion of that same fault segment would be unlikely to meaningfully load the subduction zone. A 4.9 releases roughly 1,000th of the energy of a magnitude 7. This isn't a close call in the physics. It isn't anywhere near the line. The offshore sequence did not trigger Cascadia. What it did do was highlight something more interesting. And it comes down to 3 physically plausible explanations for why events on separate fault systems showed up so close together in time. The first is pure coincidence. Both regions are seismically active on their own, and 90 minutes between 2 unrelated clusters of small earthquakes is precisely what independent tectonic processes look like when you happen to be watching both simultaneously. The second is dynamic triggering, where seismic waves from one earthquake pass through the crust and shake a nearby fault that's already sitting close to failure. This is real and well documented, but it almost always follows much larger earthquakes, and the triggered events it produces are typically tiny. So if dynamic triggering played any role here, the small one, 4 and 2. 0 were likely the entire visible effect. The third possibility is a shared driver, some broader pulse of internal deformation within the plate itself, showing up simultaneously on multiple fault structures. The plate in question here is one of the most internally deformed on Earth, squeezed between three separate systems. So a deformation pulse showing up on several structures at once is plausible in principle. It's also the least testable of the three explanations. Nobody can currently prove or disprove it with the available data. But arguably, the most revealing part of this entire sequence wasn't something that happened. It was something that didn't. Deep beneath the locked portion of Cascadia that will eventually fail in a megathrust rupture, the plate interface releases built-up strain in a completely different way than a conventional earthquake, through something called episodic tremor and slip. During these episodes, the fault creeps slowly over days or weeks, accompanied by a faint, continuous seismic hum called tectonic tremor. Nobody has ever felt one of these events directly. They recur along different portions of the margin roughly every 8 to 22 months, depending on location, and monitoring networks track this tremor continuously and publicly, because it's one of the very few windows scientists have into what the deep part of that fault is actually doing right now. So here's essentially the test the monitoring network ran. In the hours after the offshore sequence, if those events had in any real way loaded or disturbed the nearby portion of the Cascadia margin, one plausible signature would have been a burst of new tremor activity in the deep zone beneath that same stretch of coastline in the hours that followed. That isn't what happened. Instead, the tremor activity recorded that evening was concentrated hundreds of miles away, in a cluster near the northern end of the margin. Directly adjacent to where the offshore earthquakes actually hit, the deep zone stayed quiet. And that silence turns out to be one of the more informative data points in the whole sequence. There are a few honest ways to read it. The simplest is that nothing was transferred, so nothing responded, which lines up exactly with the physics already discussed. Another is that this particular segment of the margin simply isn't due for one of its slow slip episodes right now. These events come and go on their own separate schedules, and if the South isn't currently in its window, it wouldn't show a tremor response to much of anything, even a considerably larger earthquake. A third possibility is that a response occurred, but fell below what the instruments could detect, since the monitoring network is land-based and offshore signals weaken with distance. And a fourth possibility, the genuinely interesting one that researchers are careful not to overstate, is that this segment of the deep zone simply isn't producing slow slip activity at all right now. That would matter, because slow slip in the deep zone is the mechanism by which stress gets quietly transferred upward onto the locked portion of the fault above it. This last reading is the least supported by current data, and nobody working seriously in the field is claiming it based on a single quiet night of observation. Here's where the story stops being about one earthquake sequence and becomes something considerably larger, because the most consequential development connected to all of this isn't anything that happened this week. It's a piece of research published earlier this year that fundamentally changes how seriously the broader threat sitting beneath this coastline needs to be taken. And it has almost nothing to do with when Cascadia will finally rupture. It has to do with what might happen immediately afterward. For decades, the standard understanding of a major Cascadia earthquake treated it as a singular, if catastrophic, event. The fault ruptures. The coastline shakes violently for several minutes. A massive tsunami follows. The immediate crisis is horrific, but geographically contained to the Pacific Northwest. And eventually, recovery begins. That's been the working assumption behind most regional disaster planning for years. Earlier this year, a study published in the peer-reviewed journal Geosphere, led by a paleoseismologist at Oregon State University who has spent decades studying this exact fault system, presented evidence that complicates that picture considerably, and not in a direction anyone particularly wanted. The origin story of this research is almost accidental. Back in 1999, a research cruise collecting deep sea sediment cores off Oregon and Northern California made a navigational error that carried the ship roughly 55 miles south of its intended target, out of the Cascadia zone entirely and into the territory of the San Andreas fault system. Rather than waste the detour, the crew decided to pull a core there anyway. What came up didn't make sense under normal conditions. Sediment layers deposited by underwater landslides, called turbidites, normally follow a predictable structure, with coarser material settling first at the bottom and finer material settling more slowly on top. This particular core showed the opposite pattern: fine material at the bottom, coarser material above it. The team's interpretation was that the lower, finer layer had been deposited by a large Cascadia earthquake, and the coarser layer above it had been laid down by a separate, subsequent rupture on the nearby San Andreas system, arriving before the sediment from the first event had even finished settling. They called this structure a doublet, and then they went looking for more of them. Across roughly 300 years of sediment cores collected on both sides of Cape Mendocino, the pattern that emerged has become one of the most talked about findings in West Coast seismology in recent memory. 10 Cascadia turbidite layers over that span are closely associated in time with earthquake deposits on the northern San Andreas fault, separated on average by roughly 60 years. In at least 3 instances over the past 1,500 years, including the confirmed 1700 event, researchers believe the two ruptures were separated not by decades, but by minutes to hours. It's worth being precise about what this research does and doesn't claim, because overstating it would be its own kind of disservice to the science. The researchers are not claiming that every past Cascadia rupture triggered a San Andreas earthquake, and they are absolutely not claiming that a future Cascadia rupture guarantees a domino effect. What the sediment evidence shows is a pattern, a correlation appearing across multiple ancient events, strong enough to publish in a peer-reviewed journal and strong enough to warrant serious further investigation, but not yet definitive proof of a mechanical link that operates every single time. Still, even treated as a possibility rather than a certainty, the implications are significant enough that the lead researcher has been blunt about it. Cascadia gets described as a catastrophic event on its own, but according to this newer thinking, a solo Cascadia rupture might not actually represent the true worst case. A single Cascadia earthquake alone would already draw down emergency response resources across the entire country. If Cascadia and the northern San Andreas system were to rupture together, or within hours of each other, cities from Vancouver down through Seattle, Portland, and San Francisco could all find themselves in a simultaneous emergency within the same compressed window of time. No emergency management system anywhere is currently built to handle that. And here's the detail that connects this research directly back to the earthquake sequence that just happened. The specific segment of the Cascadia margin sitting closest to where these offshore quakes struck is also the segment where the two fault systems converge most directly. It's the segment researchers now consider to carry the highest recurrence probability, and it's the segment that has been locked and quietly accumulating stress for more than 3 centuries. Layer another recent finding on top of that. New research presented earlier this year, based on more precise seismic imaging, found that the subducting plate beneath the northern Oregon coast sits several miles shallower than earlier models had assumed. That shallower geometry increases estimated peak ground shaking during a future Cascadia rupture along the Oregon coast by somewhere in the range of 9 to 17%. The same study also identified a previously uncharacterized sedimentary basin further along the coast, the kind of geological feature that amplifies ground shaking the way a bowl of water sloshes harder than a solid surface would. Put together, these findings mean the shaking from a future Cascadia rupture is now expected to be measurably stronger along parts of the Oregon coast than earlier hazard assessments had calculated. None of these updated findings changed the underlying probability numbers this week. Not one of them. Those numbers were exactly what they are now before this earthquake sequence happened, and they'll be exactly the same next week too. Over the coming 50 years, the chance of a full margin magnitude 9 event is estimated at somewhere around 10 to 15% on a time-dependent basis. For magnitude 8 or larger specifically on the southern portion of the margin, the time-dependent probability is closer to 30%, with some research based on the offshore turbidite record, putting figures for that southern segment as high as the high 30s to low 40s over the same 50-year window. The paleoseismic record contains dozens of identified Cascadia earthquakes, stretching back roughly 10,000 years, and the interval the fault is currently sitting inside, more than 3 centuries and counting since the last full rupture, is already longer than the vast majority of intervals recorded over the last several thousand years of that record. That's the genuinely uncomfortable part of this entire story. The recent offshore sequence didn't move any of those numbers, but it also didn't reveal a fault system that's anywhere close to releasing the pressure it has been quietly accumulating since the night of January 26, 1700, a date confirmed through tree ring death dates in drowned coastal ghost forests, through layers of coastal land subsidence, through offshore sediment deposits, and through Japanese written records of a tsunami with no local earthquake to explain it, whose travel time researchers were able to calculate back to an origin point on the opposite side of the ocean. There's also what was happening on inland California faults during that same window, and it connects back to the doublet research. In the days surrounding the offshore sequence, several magnitude 4 class earthquakes rattled a fault system in northern California, including a cluster less than a minute apart, with the larger event arriving second and at shallower depth. Sequences where the bigger shock follows the smaller one are consistent with foreshock behavior, though equally consistent with an ordinary swarm that simply fizzles out. Both statements are true at once, and neither is a prediction. That fault system isn't remote countryside. It forms the northern end of a structural chain running directly south into one of the most densely populated seismic corridors in the American West, a San Andreas system that has sat comparatively quiet for well over a century since its last truly great rupture. And all three are publicly checkable in something close to real time. The first is tectonic tremor on the southern portion of the Cascadia margin. Monitoring networks update tremor maps continuously. And the open question is whether the deep zone beneath that stretch of coastline produces one of its slow slip episodes in the coming weeks, and if it does, whether that episode looks routine or unusual in its timing, duration, or location. Right now, the active tremor is concentrated far to the north. Whether the south eventually follows is the thing worth tracking. The second is the inland California fault sequence. The threshold that would genuinely shift the assessment there is a magnitude 5 or larger on that fault system, or a third distinct cluster of magnitude 4 events. The signal that separates a swarm that simply stops from a sequence that's building towards something larger is whether magnitudes keep climbing and whether activity migrates along the fault rather than repeating in the same spot. The third is simply the ongoing review of the seismic catalog itself, since some signal arrivals recorded on land during a sequence like this take time to get fully reviewed and confirmed, particularly when the nearest instruments sit hundreds of miles from an offshore source. None of this amounts to a forecast. Cascadia doesn't issue warnings, and the most scientifically honest position available right now is that this fault could remain locked and quiet for another century, or it could rupture tomorrow. And both of those outcomes are completely consistent with everything the geological and seismic record currently shows. What actually shifted this week wasn't the probability of the earthquake. What shifted was the clarity of the picture. A routine offshore sequence put the southern Cascadia corridor under closer scientific attention than usual, and what came back was a set of details serious researchers aren't simply dismissing. Unusually located microseismicity right around plate interface depth, deep tremor active far to the north while the south stayed silent, inland fault activity picking up across northern California within the same general window, a locked segment now more than 3 centuries into an interval that already exceeds the vast majority of intervals recorded over the last several thousand years, and a newly published body of research establishing that this fault system may not necessarily fail in isolation. There's a version of this story a lot of headlines have chosen to tell, the kind that leads with the scariest possible number and lets the reader fill in their own worst assumptions about what it means. That version isn't especially honest, and it isn't especially useful either, because it trains people to either panic over routine seismic activity or, just as dangerously, grow numb to every earthquake alert until the genuinely significant ones stop registering at all. The more accurate version, the one that actually reflects what researchers are publishing right now, is more layered than any single headline can capture. A moderate, unremarkable earthquake sequence on a fault that produces them constantly, correctly, and quickly ruled out as posing no tsunami threat, sitting inside a much broader regional picture that scientists are only now beginning to fully understand. One where the true worst-case scenario for this stretch of coastline may not be a single catastrophic earthquake happening in isolation, but 2 of them, hundreds of miles apart, arriving close enough together that an entire coastline ends up fighting for survival on 2 fronts at once. If you live along the Oregon coast, the Washington coast, or the Northern California coastal zone, the practical takeaway from all of this isn't a countdown or a date. It's knowing your evacuation route before you ever need it, understanding the ground beneath your own feet, and recognizing the real difference that a few minutes of hesitation can make when the ground finally does start to move for real. That's the one thing this particular earthquake sequence actually changed, but not the underlying risk, which was exactly the same the day before it happened and remains exactly the same today, but how clearly anyone paying attention can now see the shape of what they're watching for.